Hi, this is the video that is going to be about deductivism, David HIlbert, and Finitism and the Hilbert Program. Um, this video might be a little long because there's a lot to explain here, and I want to explain it thoroughly. I don't want to mess it up. I want to explain it thoroughly. There's a video that's before this called Intro to Formalism. If you don't know what formalism is, I suggest that you should go a video backward and see that, or at least watch it for a little bit to get a definition of formalism, or you can look it up yourself, whichever. Or if you know what formalism, then nice. Deductivism is, well, it came in the Foundations of Geometry by David HIlbert, and deductivism is one stage which allows him to move from that towards his axiomatization of all of the branches of mathematics. Now, I would like to note that Hilbert's work on geometry and his work on philosophy of mathematics itself arises from his desire to detach geometry from spatial intuition. Because if any of you know Kant in the Critique of Pure Reason has a transcendental aesthetic in there, where he discusses that geometry and mathematics that geometry is describing spatial intuition, or geometry is it essentially is mathematical and scientific explanation of our spatial intuition. And he said that about time as well, and that time and our intuition of time, our temporal intuition, is explained by arithmetic. Now, I also have a video quite a little ways backward that discusses non-Euclidean geometry. Now, Euclidean, I explain in that video quite a ways back about both the Lobachevskian and the Riemannian geometries, and how they kind of show it basically looks at the 5 postulates of Euclidean geometry and touches on the 5th postulate and how it can't be proven, and that relates to this because I'm going to talk about implicit definition and all that, because it's pretty important, actually. So I want to first discuss deductivism. Deductivism is not the Hilbert program itself, but it's very important with this. It's in contemporary terms, for the application of a branch like arithmetic to succeed, the rules of the game cannot be arbitrary, but must constitute logical consequences. Now, this is Frege, and he's looking at game formalism, and he has some things to say about it. The advent of rigorous deductive systems, thanks in large part to Frege, suggests that a tempting philosophy that has something in common with game formalism but avoids a particular pitfall. A deductivist accepts Frege's point that rules of instruments must preserve truth, but she insists that the axioms of various mathematical theories be treated as if they were arbitrarily stipulated. The idea is that the practice of mathematics consists of determining logical consequences of otherwise uninterpreted axioms. The mathematician is free to regard the axioms and the theorems of mathematics as meaningless, or to give them an interpretation at will. To articulate this view rigorously, one would distinguish the logical terms like and, if then, there exists, and for all, from the non-logical or specifically mathematical terminology such as number, point, set, line. The logical terminology is understood with its normal meaning, while the non-logical terminology is left uninterpreted, or is treated as if it were uninterpreted. Let phi, the Greek letter phi, be a theorem of, say, arithmetic. According to deductivism, the content of phi is that phi follows from the axioms of arithmetic. Deductivism is sometimes called if-thenism, and I'll explain why. The affinity between... Now I'm still using this book here as like a help me. It's kind of like a guide right now. The affinity between game formalism and deductivism results from the development of logical systems that can be operated like a calculus, as Frege put it. Deductivism is consonant with the slogan that logic is topic neutral. From the modern model theoretic point of view, if an inference from a set of premises x to a conclusion phi is valid, then phi is true under any interpretation that makes all of the premises x true. The idea behind deductivism is to ignore the interpretation and stick to the inferences. Like game formalists, our deductivist proposes clean answers to philosophical questions. What is mathematics about? Nothing, or it can be regarded as nothing. What is mathematical knowledge? It is knowledge of what follows from what. It is knowledge of what follows from what. So it's about deductivism is about inferences. Like the theorem phi. The content of phi is that phi follows from the axioms of arithmetic, phi being a theorem. So it's a if-then kind of thing. Looking at the inferences. Like the game formalists, our deductivist proposes clean answers to philosophical questions. What is okay, I wrote that already. Shit. Deductivism is a philosophy that goes well with developments in the foundation of mathematics, especially geometry, during the 19th and early 20th centuries. The crucial event included the advent and success of analytic geometry with projective geometry as a response. The attempt to accommodate ideal and imaginary elements such as points at infinity, the development of n-dimensional geometry, and the assimilation of non-Euclidean geometry to mainstream mathematics alongside, not replacing Euclidean geometry. These themes helped to undermine the Kantian thesis that mathematics is tied to intuition of space and time. Okay, so this is an if-thenism that we're looking at. We're looking at inferences, pretty much, in the deductivist idea. And this goes on with the theme of formalism that we're looking at the characters and their relations. There are the linguistic characters and their relations, and the leaving the interpretations out for now. And again, this is helping to detach the idea of mathematics and geometry, attaching that to spatial and temporal intuition, and taking that idea away, because it's not about this. It's not about this stuff I'm seeing and touching. It's theorems and how they follow from mathematical axioms. Okay. Now this is this is a statement by Morris Posh. If geometry is to be truly deductive, the process of inference must be independent in all its parts from the meaning of geometrical concepts, just as it must be independent of the diagrams. Only the relations specified in the propositions and definitions may legitimately be taken into account. During the deduction is useful and legitimate, but in no way necessary to think of the meanings of the terms. In fact, if it is necessary to do so, the inadequacy of the proof is made manifest. Okay, and then it is Now, this discussion of deductivism should show where this is moving. It should, and thought about what the idea of formalism is, and see this idea of deductivism should show where this is all going. David Hilbert's work in geometry around the turn of the 20th century represents the culmination of these foundational developments. The program executed in his Greenlog and der Geometrie marked an end to an essential role for intuition in geometry. Although spatial intuition or observation remains the source of axioms in Euclidean geometry, in Hilbert's writing, the role of intuition in observation is explicitly limited to motivation and is heuristic. Once the axiom has been formulated, intuition and observation are banished. They are not part of mathematics. Okay. And this is something that Hilbert said when in a Berlin translation in 1891. One must be able to say, instead of points, straight lines, and planes, proper axiomatization of he's talking about proper axiomatization of geometry. One must always be able to say, instead of points, straight lines, and planes, tables, chairs, and beer mugs. Okay, this is where we get to. This is kind of hard to explain. That's why I'm kind of going through Shapiro's writing rather than explaining it myself, because it's kind of hard to explain. But from here on out, I'm going to explain it a little more. Okay, now this is where he explains the idea of an implicit definition. We think of points, straight lines, and planes as having certain mutual relations, which we indicate by means of such words as are situated, between, parallel, congruent, and continuous, etc. The complete and exact description of these relations follows as a consequence of the axioms of geometry. To be sure, Hilbert also says that the axioms express certain related fundamental facts of our intuition. But in the subsequent development of the book, all that remains of the intuitive content is to use words like point, line, and so on. This is Paul René's summing up the aims of David Hilbert. The main feature of Hilbert's axiomatization of geometry is that the axiomatic method is presented and practiced in the spirit of the abstract conception of mathematics that arose at the end of the 19th century, and which has generally been adopted in modern mathematics. It consists in abstracting from the intuitive meaning of the terms, and in understanding the assertions, theorems of the axiomatized theory in a hypothetical sense, that is, as holding true for any interpretation for which the axioms are satisfied. Thus, an axiom system is regarded not as a system of statements about a subject matter, but as a system of conditions for what might be called a relational structure. On this conception of axiomatics, logical reasoning on the basis of the axioms used not merely as a means of assisting intuition in the study of spatial figures, rather their logical dependencies are considered for their own sake, and is insisted that in reasoning we should rely on those properties of a figure that are either explicitly assumed or follow logically from the assumption in axioms. And this is the second of Hilbert's famous mathematical problems. Extend the deductivist to approach every corner of mathematics. When we are engaged in investigating the foundations of a science, we must set up a system of axioms which contains, this is by Hilbert, by the way, which contains an exact and incomplete description of the relations subsisting between the elementary ideas of that science. The axioms set up are, at the same time, the definitions of those elementary ideas. Okay, so I want to kind of explain what I've just read. The whole idea of deductivism is that it's about the inferences, essentially talking about the relations between the things, between the characters. Deductivism is called if-thenism because it's looking at inferences. And he says that Hilbert says that deductivism extends this extends the deductivist approach to every corner of mathematics. Now, this is to axiomatize each branch. An axiom essentially is a rule, or like the Dedekind piano axioms. Go look those up if you want to see like how those axioms work. Those are axioms for those are rules of mathematics. Now, Frege did some work in that too, but he was not trying to axiomatize branches and thus the whole system of mathematics, but he had axioms for how logic and thus for him mathematics work. Axioms are rules, and in practice, axioms are rules as to how linguistic characters are related to each other, and thus with those axioms, given certain truths, like even with the truths of non-Euclidean geometries, one can do certain things to manipulate those axioms in certain practice to get what you are looking for, I guess. Now, a big thing that is discussed here is something called meta-mathematics. Meta-mathematics is discussed as things about the systems. Meta-mathematics is mathematics or rules or applications, or it's mostly to prove things about formal systems. And this is itself a branch of mathematics. Now, you might think, well, meta-mathematics is outside of the branches of mathematics, but what Hilbert does is he brings that back into the other branches and tries to axiomatize meta-mathematics as well as the rest of mathematics. Presumably, this meta-mathematics is not itself the derivation of theorems from axioms regarded as meaningless. The goal of meta-mathematics is to shed light on the subject matter, namely formal language and axiomatizations. Thus, meta-mathematics seems to be an exception to the theme of deductivism and game formalism, which holds that mathematics need have no subject matter. So the problem here is that it's the whole idea of meta-mathematics is that it's about a certain thing, about proving things about formal systems. One option would be for the deductivist to hold that meta-mathematics is not mathematics, but this is close to an oxymoron. Meta-mathematics has the same appearances and methods as any other branch. To be sure, meta-mathematics can be and subsequently was formalized. To be consistent, our deductivist should propose that mathematics in meta-mathematics is just the derivation of consequences from the axioms of this meta-mathematics, which these axioms regarded as meaningless. The application of meta-mathematics to formal languages and deductive systems is irrelevant to its essence as a branch. Just as arithmetic can be applied to counting, meta-mathematics can be applied to deductive systems. The role and importance of meta-mathematics varies among the formalist authors. And a lot of what Shapiro does in this chapter, he discusses the correspondence between Frege and Hilbert. Essentially, what Frege would say about Hilbert's system is that it's like an equation with a lot of unknowns, like the whole idea of implicit definition, which I'll explain better here in this video. Essentially, Frege would say that in this axiomatization and saying that it's about the rules, the axioms, the linguistic characters, and the manipulation of those through those axioms is like an equation with lots of unknowns. Now, I could go into this this correspondence, but I'd like to shorten this video a little bit. But essentially, I mean, they have different ideas, and they have different goals, even though they are both probably they were really amazing minds, and that this is actually pretty interesting. But that whole correspondence pretty much comes down to their being very different minds with very different ideas and very different goals. As Frege's goal was to show how mathematics is reducible to logic and create a system out of that, and Hilbert's idea was to be able to axiomatize every single branch and create a whole formal system. Okay. Okay. Now I'm going to explain the idea of Finitism in the Hilbert Program. Deductivism played a huge part in all this, but Finitism is pretty much the way that it's all being axiomatized. Okay. Whatever its philosophical merit, the Hilbert Program led to a fruitful era of mathematics that thrives today. For Hilbert, the program had an explicit epistemic purpose. The goal of my theory is to establish once and for all the certitude of mathematical methods. It would build on the early work of axiomatizing branches of mathematics, as well as the monumental efforts of logicists like Frege in developing rigorous logical systems. There is a completely satisfactory way of avoiding the paradoxes without betraying our science. The desires and attitudes which help us find this way are these. 1. We will carefully investigate fruitful definitions and deductive methods. We will nurse them, strengthen them, and make them useful. No one shall drive us out of the paradise which Cantor has created for us, and that can be explained in a certain way because of Cantor's set theory. 2. We must establish throughout mathematics the same certitude for our deductions as exists in ordinary elementary number theory, which no one doubts, and where contradictions and paradoxes arise only through our own carelessness. The idea behind the program is to carefully and rigorously formalize each branch of mathematics together with its logic, and then to study the formal systems to make sure they are coherent. To describe the program, we begin with its core, which is sometimes called finitary arithmetic. Most emphatically, finitary arithmetic is not understood as a meaningless game like chess, or as the deduction of the consequences from meaningless axioms. On the contrary, the assertions of finitary arithmetic are meaningful, and they have a subject matter. The formulas of finitary arithmetic are equations like the type 2 plus 3 equals 5, and so on. Notice that so far, the only statements to be considered are those that refer to specific natural numbers, and that all of the properties and relations mentioned are effectively decidable in the sense that there's an algorithm that computes whether the properties and relations hold. Consider the following two sentences. 1, there is a p. There's a number p greater than 100. Less than 101 with the exclamation point. I forget in my math classes what we would call that. Plus 2 such that p is prime. There's a number p greater than 100 such that both p and p plus 2 are prime. Both of these contain a quantifier. There is a number p, but there is a difference between them. So this is essentially an existential quantifier in both, but it's different. The quantifier in sentence 1 is limited to the finitely many natural numbers less than 100! Plus 2. Call this a bounded quantifier. In contrast, the quantifier in sentence 2 has no limits. The sentence 2 is there's a number p greater than 100 such that both p and p2 are prime. That has not a limit on it, but the other one does. This is called an unbounded quantifier. Hilbert regards sentences with only bounded quantifiers to be finitary, while sentences like 2 are not finitary. Our next item concerns the content of finitary arithmetic. What is it about? Apparently, the subject matter of finitary arithmetic is the natural numbers. So once again, we ask what those are. Hilbert explicitly rejected the theologist's perspective. We find ourselves in agreement with philosophers, notably Kant. Kant taught that mathematics treats a subject matter which is given independently of logic. Mathematics, therefore, can never be grounded solely on logic. Consequently, Frege's and Dedekind's attempts to do so were doomed to failure. Hilbert holds that finitary arithmetic concerns what is, in a sense, a precondition to all human thought, even logical deduction. Using Kantian language, Hilbert wrote, to think coherently at all. Something must be given in conception. Certain extralogical concrete objects which are intuited as indirectly experienced prior to all thinking. For logical deduction to be certain, we must be able to see every aspect of these objects, and their properties, differences, sequences, and contiguities must be given, together with the objects themselves, as something which cannot be reduced to something else. This is the basic philosophy which I find necessary, not just for mathematics, but for all scientific thinking, understanding, and communicating. Hilbert, so this is pretty much in sight of this system relating to something concrete, something extra logical. This is why this finitary arithmetic is important. Hilbert proposed that the subject matter of finitary arithmetic is the concrete symbols themselves, whose structure is immediately clear and recognizable. He proposed that in finitary arithmetic we identify the natural numbers with the numerical symbols. And he has this here. He emphasized that, so understood, each numerical symbol is intuitively recognizable by the fact that it contains only ones. The symbol type 2 is then introduced as an abbreviation of the lines 2, etc. So the inequality 3 is greater than 2 serves to communicate the fact that the symbol 3, i.e. the 3 lines, is longer than the symbol 2, i.e. the lines 2. Or in other words, that the latter symbol is proper part of the former. Despite of the use of the word concrete, Hilbert intends the character studied in finitary arithmetic to be understood as more as abstract types than as physical tokens. The physical hunk of ink or burnt toner 2 is not a part of the physical hunk 3. The ideal of mathematics to be treated formally, pretty much along the lines of game formulas. The syntax and rules of inference for each branch of ideal mathematics are to be formulated explicitly as the branch is to be pursued as if it were just a game of Greek characters. Hilbert says, a material deduction is thus replaced by a formal procedure governed by rules. These rules are those of the deductive systems developed by logicians like Frege. I want to explain an implicit definition. An implicit definition is defining a certain sentence at all, any kind, in terms of its relations, not in terms. Let's say we have a certain. Let's say if we have the sentence, how to phrase this. Bachelors are unmarried men. Let's try to use that. It's not focusing on the meaning of the word unmarried man. It's not focusing on the meaning of the word bachelor either, but it's looking on how they're related. Let's take the possible. Looking at any kind of mathematical sentence, it's not looking at the meaning of the term. It's not looking at the meaning of the term 5, or it's not looking at the meanings of any of them. It's looking at the relations of them, and it's looking at the relations and the characters there mostly. And it's looking at any definition that way. This is that idea is important because that ties into the non-Euclidean geometries, and it also ties into the Hilbert's program to axiomatize all of mathematics and the little deductivist idea of inferences. Phi is a theorem given a consequence of certain axioms. Okay. Essentially, this is a 4-stage explanation of what Hilbert has going on here by John von Neumann. Provides a succinct summary of the Hilbert program as involving 4 stages. 1, to enumerate, to figure out all the symbols used in mathematics and logic. 2, to characterize unambiguously all the combination of these symbols which represent statements classified as meaningful in classical mathematics. These combinations are called formulas. 3, to supply a construction procedure which enables us to construct successively all the formulas which correspond to provable statements of classical mathematics. This procedure accordingly is called proving. 4, to show in a finitary way that those formulas which correspond to statements of classical mathematics, which can be checked by finitary arithmetical methods, can be proved by the process described in 3, if and only if the check of the corresponding statement shows to be true. And Shapiro says that item 4, the crucial culmination proves to be problematic. So essentially, that's looking at the only way that it can all be axiomatized is if it's looked at in a formless way, if it's a formal system, if it's as if every sentence in mathematics is looked at implicitly. Like any kind of sentence, 5 plus 7 is looked at implicitly, or anything has to be looked at implicitly, and each concrete thing, each token looked at as a linguistic character that is set in a certain way, and it's only understood in terms of the relations. And then think about that. Like, if one can look at all of mathematics and every single mathematical sentence in terms of its relations to each other and the linguistic characters, not looking at anything else, looking at the relations of all of everything there. Using that, it's kind of understandable to see how Hilbert could have, done that. It's conceivable to see how, given that, each branch can be axiomatized into a set of axioms, rules, things that are constant for geometry, or for a group of axioms for geometry, rules that are always going to be there for geometry, they're constants. As for every other branch, like even mathematics, he took that metamathematics and put that into his whole formal system. So we're talking about the whole system of mathematics being formally systematized and axiomatized. That is, I would think, probably one of the. This probably has to be my favorite here. Now, if you have a question as to how this relates to non-Euclidean geometries, I can explain that if you really need me to in more depth. But just to think about all of that, the idea of implicit definitions, of deductivism, the if-thenism, and all of that with respect to every mathematical sentence, and systematized and axiomatized together. It's perfect, I think. It's a perfect idea until we come to a certain problem, which is a problem according to Kurt Gödel. This is 1931. He dealt a death blow. Let T be a formal deductive system that contains a certain amount of arithmetic. Assume that the syntax T is effective in the sense that there's an algorithm that determines whether a given sequence of characters is a grammatical formula, and an algorithm that determines whether a given sequence of formulas is legitimate deduction in T. Arguably, these conditions are essential for T to play a role in the Hilbert Program. Under these assumptions, Gödel showed that there's a sentence G in a language T. So we have a language T. We have a sentence G. 1. This is the first incompleteness theorem of Gödel. If T is consistent, then G is not a theorem of T. If T is consistent, then G is not a theorem of T. 2. If T has a property a bit stronger than T, then the negation of G is not a theorem of T. So we're talking about in this language T, a property stronger than consistency, or let's say it's a phi, or let's say it's a alpha contingency that's stronger than consistency, then that would mean that, okay, let's think about this first one here. This is kind of hard to understand, so bear with me. T is a certain language, and G is a sentence in it, and T, as it is, consistent. G is not a theorem of T at all. So then we have this stronger property, let's say alpha consistency. Then the negation of G is not a theorem of T. That is, if T is alpha consistent, then it does not decide G one way or another. This result is known as Gödel's first incompleteness theorem. It's one of the major intellectual achievements of the 20th century. The formula G has the form of a finitary statement using letters for generality. Roughly speaking, G is a formalization of a statement that G is not provable in T. So if T is consistent, then G is true but not provable. Gödel's result thus dashes the hope of finding a single formal system that captures all of classical mathematics, or even all of arithmetic. If someone puts forward a candidate for such a formal system, then we can find a sentence that the system does not decide, although we can say that the sentence is true. If you don't understand, if you don't understand how that, because the Hilbert system is one system of the whole, all the branches of mathematics, all of it. Now this kind of undermines the idea of there possibly being a whole system, a whole formal system, axiomatizing and systematizing all of the branches of mathematics. This breaks that whole hope down, all of it down. I'm going to explain this a little bit better. G is a sentence in the language of T, and the language T being consistent, then G is not a theorem of it. And there's a property, T having a property stronger than consistency, then the negation of G is neither a theorem of T. That kind of attacks that whole idea of a single formal system of mathematics, of every branch axiomatized into one whole system, a whole thing, formally systematized and axiomatized. It breaks the whole thing down. The second incompleteness theorem. Okay, this result does not indicate trouble for the Hilbert program. Let PA be a formalization of ideal arithmetic, say the classical theory of the natural numbers. The Hilbert program requires a finitary proof of the consistency of PA. But the second incompleteness theorem is that if PA is in fact consistent, then a straightforward statement of the consistency of PA is not derivable in PA itself, let alone in the finitary portion of PA. The same goes for any formal system so long as it contains a certain amount of arithmetic. So this second theorem shows a little bit better the whole problem with this whole single system. The second incompleteness theorem is that if PA, the formalization of an ideal arithmetic, if it is in fact consistent, then a straightforward statement of the consistency of PA is not derivable in PA itself. So if we have this Hilbert program, this whole system, then a proof of its consistency cannot be derived in itself, because this is the whole system of mathematics, the whole system. It's not possible to have a proof for consistency of PA within that system. Can you see how that wouldn't work? It's like one saying that you are not lying when you could pretty much be lying. It's just like a person cannot prove to you that, I don't know, that's not a very good example. But think about that. One system cannot prove for itself its own consistency. it seems the consistency cannot be proved in the system itself, let alone in a more secure system. And this is by this is Gödel paraphrasing Paul Bernays. Since the consistency of a system cannot be proved using means of proof weaker than those of the system itself, it is necessary to go beyond the framework of what is, in Hilbert's sense, finitary mathematics if one wants to prove the consistency of classical mathematics, or even that of classical number theory. In the proofs of what we make use of insights that spring not from the combinatorial spatiotemporal properties of the sign combinations, but only from their meaning. Gödel pointed out since we have no precise notion of what it means to be evident, we cannot rigorously prove Bernays' claim. But Gödel added that there can be no doubt that it is correct. So this is options, given this. Now, can you see how both of those theorems crumbles the whole system? If you don't, and you want to either Google it or let me know, and I can explain any of this better. If you want, especially if you want to know how the non-Euclidean geometry relates to this, that definitely let me know. Yeah, this is all of it. This is given the theorem, the incompleteness theorems. This is what's left for the Hilbert program and the formal systems. Two options. One is to challenge the formalization of consistency used in the proof of the second incompleteness theorem. To challenge the formalization of consistency used in the proof of the second incompleteness theorem. There are other ways to express consistency properties that escape the second incompleteness theorem. The issue then turns on just what counts as expressing consistency and what a proof of consistency must show in order to meet the epistemic goals of the Hilbert program. A second option would be to show or claim that the methodology of the finitary arithmetic cannot be captured in PA or in any other formalized theory. That is, even though the purpose of a branch of ideal mathematics is to streamline the derivation of the finitary statements, the proof methods of any given formalized theory do not include every finitary proof method. The thesis is that finitary arithmetic is inherently informal. Okay. That is from Hilbert through Gödel. And from here on out in this playlist of philosophy of mathematics, I'm going to discuss a little bit, and I'm not sure how much, I'm going to discuss the third one, intuitionism, and then I'll probably go on to things like the Quine-Putnam indispensability and structuralism and such. So yeah.